So the goal of my talk today is, if you look at ESXtop and if you look at the ESXtop counters, in a lot of ways, it may look like this for you. And my goal is to make you a Neo, and my goal is to make sense of ESXtop. So this is actually a very interesting analogy because you can infer a lot of things which is happening inside a VM by just observing ESXtop. You don't even need a remote console session into the VM to know what's going on. If you have a trained eye, you can just look at ESXtop counters and you can tell many things about the VM. You can say what exactly the VM is currently doing, whether it's booting, whether it's shutting down, whether it's running a graphical workload, whether it's running a CPU workload, whether it's memory workload. All of those characteristics you can define, and you can make sense out of it just by looking at the ESXtop. So that's my goal. So in the previous years when I gave this talk, I have focused more on troubleshooting scenarios. But this year my focus is going to be how do we understand the inner workings of ESX, and how do you understand how your guest operating system is behaving by looking at the ESXtop counter. So that's the theme of today's talk. And these are the topics that I'm going to be covering today. To start off, I'm going to say, how do you manage data in ESXtop? Because ESXtop generates a huge amount of data. So how are you going to manage that? I want to talk about memory usage, some cool new features with regards to NUMA. I'm going to introduce a concept called user worlds and why user worlds are so important when it comes to performance troubleshooting. CPU usage, this is especially important on all the modern processors which has processor clock frequency scaling, which makes understanding CPU usage a little bit tricky. And then I'm going to talk about two different types of host cache and how the effects of the host cache can be observed from ESXtop. And I'm going to conclude with a section on SRIOV, which is a new feature we added in ESX 5.1. And I'm going to say how you're going to observe this feature in ESXtop. Okay, so first let's start for managing data. If you have hundreds of VMs and if you have hundreds of hosts, or I would say anything more than 100 VMs, I would recommend skip ESXtop, just use vCenter operations. Because ESXtop collects a lot of statistics, but it's not a tool designed for collecting statistics from multiple machines, correlating them, doing analytics on top of them, and those kind of stuff. So if you want to just locate the problem, if you want to know, I have 1,000 VMs, which VM is misbehaving? What is the problem there? Just get a high-level view, then vCenter operation is the right tool. And vCenter operation just not alone does performance related stuff, it also does capacity planning, it also does configuration management, because they all tie in together into one single piece. When you're doing performance measurement, you're also looking at capacity, and when you're looking at performance troubleshooting, configuration is also an important aspect, because if some configuration has changed, that could trigger a performance problem as well. So it kind of bundles everything together in an integrated product. With that said, let's take a look at ESXtop and what it offers. So if you're a user, not a heavy user of ESXtop, first thing is probably you shouldn't be attending this talk because this is meant for hardcore ESXtop users. But let's say you're a casual user, you don't use it that often, but you just wanted to get a quick glimpse of what's going on, then you can just launch ESXtop. You can get the uptime of the ESX host. You can get a quick summary of how many VMs are currently running and how many vCPUs all of these VMs have. Then we show a bunch of counters. And these counters could have all sort of values. It could have values ranging from 0 to like 13,000 or 16,000. It could have values from all sort of ranges. So sometimes when you look at this, it can become, what the hell is this? Why would I have such a huge value? Percentage, shouldn't that be supposed to be 0 to 100? Why it's like 0 to 14,000, right? So you might see those numbers like this. I'll cover this later, why we show it in this way. And then you might see some counters which may not even have value in it. It might just show a blank state. So the thing is, some of these values will show up in a different view. So what you're seeing right now is a consolidated view. Now you can break this down into a detailed view for each of these items, and then some of these counters will have value when you break them down. So that's kind of the high-level pitch on what ESXtop has when you launch it. So the thing is, ESXtop is an N-curses application, so which means you need to have the right terminal settings. Now, if you set your terminal type to be anything other than Xterm, then ESXtop is will run in a batch mode. So basically, it'll dump CSV file into the screen, which is probably not what you want. So make sure you set the right terminal settings. The terminal settings are set correctly in ESX, but let's say you're using Mac terminal and doing SSH into ESX, then you may see a wrong terminal type. So in that case, you may have to correct this. Second thing is, I highly recommend using multiple monitors if you want to run ESXtop, because it has a lot of counters and you may not be able to see everything in a single screen. So if you really want a triple monitor setup or a quad monitor setup, and if you're an ESXtop user, go talk to your manager, and this might be a chance to grab some additional monitors. So that's fine. Yes, you can have a big screen. You can have big screen resolution. You can see a lot of counters. But how about situations where you really want to limit your view? You don't want to see all this clutter, right? Very simple. There's a keystroke you can press F called for field selection. Once you press F, you can select the fields that you're interested in, and only those fields will show up. And then you can also limit the rows that you're seeing by pressing the by pressing the hash key. It basically limits, you can say how many rows you want to see so that you can reduce the clutter on the screen. So these are all useful things for managing the screen. Now, rest of my talk, I've used both these options, the field selection keys and the hash, to limit the view, so that I am presenting a screenshot which is easy to understand. So I haven't given, in the slides, I don't say which fields I've selected. That's sort of an exercise for you guys to try it out at home. It'll be fun to figure out where these counters are there in different screens. So I just want to put that out. All right, how about managing the counters themselves, right? That's for the screen, but sometimes you may want to run ESXtop in batch mode, and you want to save those files. How about those counters? Again, you can use the fields key to select the fields that you're interested in, and then you can save the setting in the configuration file, and the next time when you launch ESXtop, it will use those configurations. So it won't collect anything which is not in the fields. Anything which you have not selected, it won't collect those counters. So that's one way you can limit the data that you're collecting. There's another way you can do, which is more powerful. You can collect everything in ESXtop, load it in perfmon, and then choose the counters that you are interested in and add them in perfmon. And you can even choose a time range that you're interested in. Let's say you collected ESXtop for 1 hour, but you're only interested in the middle 30 minutes. You can compress the time range in perfmon, and then you can export this value, export this file back to a CSV file so that you have a smaller CSV file to manage. So that's a very nifty feature to have. And then there is kind of this option, not many people are aware of this. So if you want to limit the rows or any kind of information that you're not interested in collecting, apart from the counters, but the rows themselves. So rows would be things like the number of VMs you have, the number of the various different LUNs you have, or the interrupts that you have. All those data gets collected from your ESX host, right? You may not need some of them. You may not be interested in any of these data when you're collecting in batch mode. So what you can do is you can run this export entity command, ESXtop with export entity option, and this would generate a file. You can then edit this file and prune the entries that you're not interested in. You can basically just delete the lines that you're not interested in, and then run ESXtop with import entity option, and only the lines which are present in that file, only the data for those will be collected. So you can greatly limit the data that you're collecting by using this option. And this works across different screens. So you can prune out VMs in the CPU screen. You can prune out interrupts in the interrupt screen. You can prune out LUNs in the disk screen, and so on. All right, so let's jump to understanding guest operating systems and understanding how ESX works. So first topic is memory usage. So there is this counter called granted memory. So I have this VM, Windows 7 32-bit VM. And so I just got this VM from one of my colleagues. He runs VDI testing. And I just powered on the VM. I changed the memory size to 8 gig. He had the VM memory size as 1 gig. So I changed to 8 gigs. I just powered it on. So memory size is 8 gig, right? But what happened is we were granting only 3 gigs of memory to that VM. And I know for a fact that Windows, when it boots, writes zeros, which means it touches all the memory pages that it's been given. But this Windows VM has touched only up to 3 gigs and has not proceeded anything beyond 3 gigs. So I was wondering what the hell is going on? Why Windows is not seeing more than 3 gigs? So it turns out that if you actually even go to the guest operating system for this VM, the Windows VM would see only 3 gigs. It won't see more than 3 gigs. The reason is this is a 32-bit VM. And for some reason, Windows 7 32-bit edition decided not to expose more than 3 gigs of memory. And this happens on physical machine too. This wouldn't be the case with Windows XP because they used to have PAE support. You can go beyond 3 gigs. For some reason for Windows 7, this is a behavior. So this again gives an indication that you can actually observe how much of the memory the guest OS is actually seeing by looking at this counter. So you know that whether you have over-provisioned your memory size for your VM. So I installed another VM, 64-bit VM. Mem size is 8 gigs. And the granted memory is 8 gig, right? Everything looks fine. So I left this VM for some time. I came back later. Same Windows 7 VM. Now the granted memory is reduced to 2.4 gigs. It's not 8 gigs anymore. So what happened in this case? Does it mean the guest is not seeing 8 gigs? No, I know for the fact that guest sees 8 gigs. So what happened in this case is we actually ballooned out memory pages from this VM. And when we ballooned out those memory pages VM, it's not part of the granted memory count anymore. So keep an eye on balloon pages as well when you're looking at the granted memory pages. So that's the kind of a takeaway, right? So obviously for this talk, this is an experiment that I did. It's not like a thing that happened and then I purposely did this experiment, right? The way I did this experiment is by setting memory limits. So I changed the VM's memory limit. The default is unlimited. I changed it to 3 gigabytes. And I know it's an 8 gigabyte VM. So then I was trying to get the screenshot and see whether I can induce this, whether the granted memory reduces. It turns out it didn't reduce. It was still 8 gigs. I was like, okay, I actually forcefully set the limit to 3 gigs. The granted memory should reduce to 3 gig, but it did not. So the reason is bulk of the guest OS memory pages were 0 pages. As I said before, Windows writes zeros when it boots up. So they're all 0 pages. So 0 pages are not consumed by the host. We don't allocate 0 pages. We just point 1 0 page for every 0 page the guest OS is requesting. So we save a lot of memory by using that technique, right? So actually, we didn't grant that much amount of memory. I mean, we granted memory to the guest operating system, but the limits were for the consumed memory of the VM. And the consumed memory does not include the 0 memory. So what I have to do next is I have to increase the limit to 1 gigabyte so that I'm putting a lot more pressure on the memory so that my limits is below the consumed memory of the VM. And at that point in time, granted memory dropped, ballooning went up, so everything was fine. Everything was as expected. So keep that in mind that the various ways that we try to save memory, and 0 pages is one of the very common technique that we use. And that explains why we don't have to, even though the guest OS is an 8 gig and the guest OS touch all of its 8 gig, we don't have to actually allocate 8 gigs of memory for the VM. All right, the next topic is active memory. So here I have a bunch of VMs. And I actually grabbed this screenshot from one of my colleagues. He's actually sitting in the audience. He was in the keynote. He was doing this demo for using social cast for virtual center management. So he was running a VM, the social cast VM on the top. So I was observing this VM, and I noticed that it has some active memory. The active memory was around 12%. It's not very high. It's not zero either. So there's some activity going on in terms of memory access. So when you look at the CPU screen of the same VM, there you see the CPU usage is pretty high. And this is actually is usually the case. Whenever you have active memory, whenever we detect this activity that the memory pages are being touched, you'll also likely to see the CPU activity to go up. So that is very clearly evident in this case. Now, SVGA is another benchmark which is supposed to be very memory intensive. And in this case, the SVGA VM is completely idle because it's not using that much CPU. It's using only 12% CPU. And as you could see, even though it's a SVGA VM, because it is idle, it's not touching any memory pages, so its active memory is exceedingly low. So the point I want to get across here is, if you see high active memory, you're also more likely to see high CPU usage because memory accesses corresponds to some sort of CPU activity. But let's take a slightly different example here. Here the active memory is really high, 73%, so some sort of CPU activity is going on, some benchmark is running in my case. Then the active memory drops quite significantly in this case. So there could be two things. One is the guest is becoming idle. The guest is becoming idle because it doesn't have any work to do. That I would explain why the active memory came down. But also, there's another reason why this could happen. So in this case, what happened is, when the workload was running fine, there was no ballooning going on in the guest OS. But in the second case, there was ballooning going on in the guest OS. And when ballooning goes on in the guest OS may swap. And when it swaps, it becomes more idle. And therefore, the active memory drops. So in this case, the guest is actually experiencing memory pressure, but its active memory is low. So the point I want to get across is, a lot of people use active memory as a kind of a guideline to say whether I should give more memory to the VM or whether I should give less memory to the VM, right? So be careful that active memory is also a function of the guest OS activity in terms of its idle activity or whether the guest OS is swapping. So in this case, if you're just looking at active memory and say, you know what, this is not using that much memory, let me reduce its memory even further. And if you reduce its memory even further, you're going to cause even less active memory because the guest is going to become more idle. So whenever you're observing active memory, keep it in the context of what's happening in the guest OS, and also keep an eye on the swapping activity for the VM. All right, the third topic is overhead memory. So overhead memory is the memory that ESX allocates for bookkeeping purposes to run a particular VM. And this is done for a number of things. So I'm going to give one particular example. So if you go to the UI, you can actually select how much amount of RAM you want to allocate for your virtual SVGA device. So you can say the default is 4 megabytes. You can say, okay, I'm going to give 128 megs because I'm going to run some 3D applications on it. I need a lot of virtual SVGA memory, so you can increase it. So when you actually increase this, this is now considered as an overhead memory for the VM. This is not part of the guest OS memory. The guest OS memory could be 4 gig, 8 gig, or whatever you set. But this is in addition to that, we have to allocate some memory for the SVGA device. So that actually shows up in this column called overhead user worlds. So this basically says how much of the memory was allocated for non-guest memory aspect of the VM, the overhead memory for the non-guest memory aspect of the VM. So in this case, it was like 260 megabytes for a VM which has 128 meg SVGA device, and it's like 24 megabytes for a 4 megabyte SVGA device. So this is all good, right? Then what happened is I actually switched to a different ESX host. So I was previously on ESX 4.1, then I switched to ESX 5.0. After I switched, my overhead memory dramatically reduced. So this is not by accident. This is not by some coincidence. So we have done a lot of performance work on ESX 5 and as well as on ESX 5.1 to reduce the overhead memory consumption. And one of the key things that we did is, previously any user world process or anything, the bookkeeping process that we wanted to handle, we used to reserve memory for its peak capacity so that we never have to swap them out in the worst case of a memory overcommitted scenario. Now we have the ability to selectively swap those processes. So therefore, we don't have to reserve for the peak capacity, but we reserve for what is required now, and then we decide to increase its size later. So that's why the overhead memory dropped dramatically from like almost a 2x reduction here. Then there's another category of overhead memory, which is overhead memory for the guest memory itself. Like if you're allocating a VM size is 8 gigs, we need to keep bookkeeping information for that 8 gigs of memory. If you're allocating a VM which is of 64 gigs, we need a lot more bookkeeping information. So it's a function of the memory size. And that is counted in this counter called overhead max. So overhead max actually is a combination of this bookkeeping memory for the guest VRAM as well as the overhead user world that I was saying before. So we have actually made significant progress even in reducing that. So as you see, there's dropped from 298 megs to 83 megs in this case, right? So this happens specifically if you have hardware which has support for hardware MMU. There's a feature called, Intel calls it as NPT, AMD calls it as RVI. If that feature is there in your processor, we don't have to do this bookkeeping. The hardware does the bookkeeping for us, and therefore we don't need to reserve a lot of memory. So this greatly reduces your overhead memory. So in this case, all I did was flip that option. So the option is controllable in the BIOS. So I went to the BIOS, disabled hardware MMU support, and then my overhead memory was 300 megs, and then I enabled it, it dropped down to 83 megs. And so this is an option which is available on every new Intel processor and AMD processor, and it should be enabled by default in your BIOS. But just go and doubly make sure that it's enabled, because you have significant savings in memory and as well as a significant improvement in performance. All right, so the third topic is, or the fourth topic is NUMA. So NUMA, we have a new feature called as a wide NUMA support, which we introduced in ESX 4.1. So I want to talk about that in this slide. So here, the host has 2 different NUMA nodes. Each NUMA node has 8 gigs of memory. And then I'm powering on a VM, and this VM has 2 home NUMA nodes. The NHN stands for home NUMA nodes. So it has been assigned 2 different NUMA nodes as being the home NUMA node. And the reason for that is this VM's mem size cannot be fit into a single NUMA node. So the NUMA node size there is 8 gigs, right? So if my VM memory size is 16 gigs, I cannot fit that VM in one particular NUMA node, so I need to interleave the VM's memory across 2 different NUMA nodes. So that's why it has 2 different NUMA nodes. And guest node 0 and guest node 1 basically tells you how much amount of memory is allocated in each of these NUMA nodes. So it's kind of equally split between node 0 and node 1. So we go do this the interleaving process. Every alternate page gets allocated on different NUMA nodes. And there's a counter called n%L, which says how much percentage of your memory is in the local NUMA node. And here it says 100% is in the local NUMA node, because your local NUMA nodes are both the NUMA nodes. You only have 2 NUMA nodes, and both are local for this VM because we're interleaving memory. And that's why it's 100% here. But all of this is on the physical layer. What about the guest operating system? If you go to the guest operating system and if you run this NUMA control command, you can actually see how many NUMA nodes the guest operating system is seeing. And here you will see the guest is seeing only 1 NUMA node. This is because we do not expose the NUMA topology to the guest OS. But that is changing with ESX 5.1. With ESX 5.1, if you have VCP count greater than 8, and your virtual hardware version is 8 or greater than 8, what we do is we still have the same 2 NUMA nodes, but the guest also will see 2 different NUMA nodes now. Now this helps us, the guest, to allocate memory accordingly, and we will map that memory on the physical NUMA node accordingly. So this will give you a boost in performance for a lot of applications which are very sensitive to the NUMA location. Typical applications like Oracle, or the latest version of JVM, which runs SpecJB is a benchmark, but any JVM-based workload also will benefit if you make the JVM NUMA aware. Okay, so the other concept I want to talk about is user worlds. So as I mentioned before, when you launch ESXtop, you see all this numbers which are greater than 100. So it's because we group a bunch of processes into something called as world groups. And each of these groups has a group ID, and that's what you see in the GID field. And then the NWLD counter says how many worlds are there in each of these groups. As you could see, some groups has only one world, some groups has like 160 worlds. And all these values that you see on the right side, they're all normalized for the number of worlds. So if your number of worlds is 160, the maximum that you can have is 160 into 100. That's the maximum range you can have, because these are all summary stats for all the worlds contained in that scheduling group. So that's the reason why you see these huge values for these counters. And I've seen a lot of people in the forums asking this question, why my wait time is so high? Should I be worried about my wait time? So in this case, if you see, the wait time for the system process is like 34,900, right? It's really huge. So wait time for any process includes the idle time. So seeing a really high wait time doesn't mean anything. You don't have to worry about it. So it's perfectly normal to see high wait time. Now, if you want to break this down into individual components, you can actually do this in ESXtop. You can press the E key to expand a group, and you specify the group ID, and then you can break it down into the individual worlds which are there in these world groups. Okay, so talking about these world groups, the way the world groups are organized, it's actually very similar to resource pool hierarchy that you see in vCenter. So you go and create a resource pools. Within a resource pool, you can create a sub-resource pool. You can assign resources for each of these resource pool. It has a parent-child relationship. The same exists for process running in the ESX. And they are actually treated as a resource pool. So for instance, the stuff that you are interested most of the time is virtual machines is part of this resource pool called the user resource pool. User world group, and the VMs are all part of that. And even the components of the VM, like VMX is a component, VMM is a component of the VM, even they are part of this. They also have a parent-child relationship to this for the user group. System components also are arranged in a similar fashion. So actually, if you go to the vCenter UI settings, you can edit these user groups, and you can change the reservations and change your CPU allocation, memory allocation, for these user groups. And these can come handy for some really corner performance cases. Like for instance, if your agent which is running on the ESX is not running fast for whatever reason, one of the reasons could be that it may be constrained by CPU cycles because it's part of this resource group hierarchy. So let's say if it's part of this kernel group, and if you haven't if you have set CPU limit for that kernel group, then it may not receive that much CPUs, and you might have a performance problem because of that. So I just want to give this idea and keep that in the back of mind that such an hierarchy exists, even though you don't see it in ESXtop. ESXtop shows them as a flat rows, but there is actually a hierarchy behind them, and you can also change the settings in the UI. Okay. So why I was explaining that will be evident when I come to the example. So here was a VM. This is again a VM from a VDI environment. It consumes 100% CPU. So something is going wrong, right? In this case, like, why should it consume 100%? So some performance problem is happening, so I wanted to do troubleshooting. The very first thing you should do is you should expand the VM by pressing the E key and see where the component, the 100% usage is actually coming from. Because you might be you might be actually misled thinking that this 100% is all coming from the vCPU. And you might think, okay, let me go to the guest OS and see what the CPU usage is. In this case, the guest OS was not showing any CPU usage at all. And that becomes very clear when you expand the screen, because when you expand the screen, you see the vCPU thread is not consuming any CPU at all. It's just 0%. And all the CPU usage comes from a thread called SVGA. Now, this SVGA thread is created when you enable 3D for your VM, And in this particular case, I was running a 3D enabled workload. So the VM was running a CAD application. And since it was running a CAD application, it was offloading all of its work to the 3D device. And that work is done by this SVGA thread. So that's why only this is seeing the CPU, and the actual vCPU is not getting used at all. So in this case, you can actually go and run some applications into the VM. They would run fine because they're going to run on vCPU 0, and they won't use the SVGA device. So another example of the same is, here again, the vCPU usage is very low. And if you look at the SVGA device, it's also not consuming that much CPU. But bulk of the CPU comes from another thread called as MKS. MKS stands for mouse, keyboard, and screen. So this basically consists of your screen updates and your keyboard inputs and your mouse inputs to your VM. So what was happening in this case is this VM was running a workload which was doing a lot of screen updates. So in this case, this is a VDA workload. The user was watching a video. So the video was updating the screen quite frequently. So the screen updates were causing some activity, and those were all processed by this thread. And again, the vCPU is free, so you can run a workload in the background and they will run fine. It's just that the screen updates are going to be slow because it's already doing a lot of screen updates. This is actually coming from writing to the SVGA device, because every time you update your screen, you have to write and update the pixels, and you're watching a movie at 24 frames per second, so you're doing a lot more updates. Okay, another example is about VM provisioning. So when you provision a new VM, you can actually specify what is the disk type you want. You can say the disk type could be EGA0, which means we write zeros up front instead of writing zeros lazily when you try to access the disk. So I selected thick provision VM, and I said EGA0, which means allocate all the 40 gig space and write zeros immediately and then return back. That's what this means. So when I did this, I go to the vCenter UI. The provisioning operation is taking some time. It was running really slow. So at midway point, I took the screenshot. It's 51%. So I got curious. Okay, what's going on here? Why it's kind of slow? Who's doing the I/O? I'm actually doing this operation from vCenter. So who's actually going and creating the disk in the ESX? I wanted to get that insight. First thing I did is I went to the LUN screen. From the LUN screen, you can actually look at the I/Os going through a particular data store. So this particular data store is getting 47 megabytes writes per second, which is not that bad. It's a pretty good, decent speed. So that's fine. So I want to know who's actually writing to this. Maybe there are other VMs running on the host which might be writing I/O to this guy, right? How do I know that the operation that I'm doing is doing this amount of 47 megabytes per second? So what you can do is in the LUN screen, you can actually enable a field which will show you which worlds are contributing to this particular LUN. So you actually have to expand this LUN. You have to press E and expand this LUN. Then you can break down the individual components, processes running on ESX, which is actually doing I/O on this particular LUN. So here, I noticed that the bulk of the I/O is coming from one world ID 9036. So now I got some clue. Okay, I know this world ID is doing some I/O. Let me go figure out who's actually this world ID is. So you go to the CPU screen, and I see the top 3 guys who are consuming CPU are hosty, and then there's one other VM which is running. So now I need to decide whether the I/O is coming from this VM or it's coming from hosty. So hosty is an agent which runs on ESX, and that's an agent which receives commands from your vCenter and executes those commands. So my suspicion was on the hosty because I'm provisioning it from vCenter, so the I/O should come through hosty. So what you can do is, you know the group ID of the hosty. So you go to the CPU screen, you expand that group, and once you expand the group, you see all the individual worlds which are contained within the group. And there you go. I see 9036, the same world ID which was doing all the I/O. And that's the world is also consuming CPU. So now I clearly know that this I/O is done from an agent which is running in hosty. And the agent is doing this work because I was doing a vCenter provisioning operation from a vCenter. So this is how you can track down, like for instance, if you have a script which is running and it's doing some I/O and you want to kill the script, This is the way you can find out which is the world ID which is doing the disk I/O, and you can actually kill the script. All right, CPU usage. So for CPU usage, I actually talked about this in the last year's session. So I'm going to repeat this because this topic is kind of complicated. So I'll cover this again. So here's a screenshot from the top line of your CPU screen. There are three main counters: pCPU use, pCPU util, and core util. So pCPU is basically anything on which ESX can schedule a process. It could be a logical CPU, it could be a physical CPU. We don't distinguish. The hardware doesn't allow us to distinguish, so we just schedule it, whatever processor which is available. But the hardware also tells us how many cores, physical cores it has, and it allows us to track counters for those cores separately from the physical CPUs that it sees. So in this case, I had hyperthreading enabled. Therefore, I had 2 pCPUs for every 1 physical core. Now, if you go to vCenter, the core utilization counter is actually reported, but it's reported for every physical CPU. But you only have 1 core for every 2 physical CPU when you have hyperthreading enabled. So because of that, you will see the same values getting repeated for core 0 and 1 because it's reporting this for the pCPUs but not for the cores. So this is actually, to be honest, this needs to be fixed in vCenter, but this is how it reports right now. So just be aware of that. If you have hyperthreading enabled, the core utilization values will be repeated for the logical CPUs. But it's actually reporting the utilization of this guy and not this. Okay, so you have a processor. The processor runs the rated clock frequency. We call it as P0. So if a clock frequency is 3 gigahertz, P0 is 3 gigahertz. Now you can measure usage with reference to P0. So that's what the, and then you also have Pn, which stands for a different clock frequency that the processor can operate. So even though the clock frequency is 3 gigahertz, the processor can be put down and say operate at 1.5 gigahertz. And that is denoted as Pn. So there could be many steps. You could be 2 gigahertz, 1.5, 1.25, and so on. So let's call that as Pn. Now you have 2 reference points now. Your usage could be measured with reference to the rated clock frequency, or it could be measured with reference to the current clock frequency. The one which is measured with reference to the rated clock frequency is called used. The one which is measured with reference to the current clock frequency is called as util. So this means you could have different values for used and util depending upon whether Pn is varying, whether Pn is same as P0 or Pn is different from P0. The used and util could have different values. And this happens when you have power management enabled. So to give you an example, if you go to your HP machine, they have a BIOS option, something which looks something like this. So you can go to the power regulator option. You can say that, you can say, HP, you manage power for me in the BIOS. Don't expose anything to the operating system. That's the option 1, HP dynamic power savings. Or you can say, I want the low power mode, which means put my clock frequency in the lowest P state possible. Put it in the lowest clock frequency possible. That's the second option. Third option is to not use this. Don't give me any P states. Just run at the highest clock frequency. And the fourth option is use the P states, but pass the P states to the operating system, let the OS decide what it wants to do with it. So let's say if you choose the third option, then if you go to the power screen in ESXtop, you could see all the P states. You could see P states ranging from P0 to P10. And you can also see the corresponding clock frequency associated with it. So this is P0, and this is P10 or something. So you can see the entire range of clock frequency this could operate on. And this screen basically shows the residency time in different P states. So if you look at it, these processors are in P10, which means they are conserving power. They are operating at the lowest clock frequency because they're idle, completely idle. How do you know they're idle? You see the used and util here, they're completely idle. But when they are getting used, the P state will jump from P10 to P0 because when you're actively using the P CPUs, you want to be at the highest clock frequency possible. So this is automatically done by an algorithm which we have in ESX, and you can control the behavior of the algorithm in vCenter too. The default algorithm tries to balance between performance versus power management trade-off. But if you're doing benchmarking or if you don't care about power, you only care about performance, you can disable that in ESX. Okay. The other concept is called core sharing. So in core sharing, we can talk about 3 different scenarios. So this is a very simple scenario. You have 2 physical cores, so which means they have 2 execution units that we call as PCPUs. Let's say you have 2 VMs running, each of them are using a separate core, everything is fine. So in this case, used is 100, run is 100, everything is fine. So you're using completely different cores. Now let's say you have enabled hyperthreading. So now for every physical core, we have been given 2 execution units. So you have 2 PCPUs for every physical core. And you have 2 VMs. Now these VMs could run on different logical CPUs. Let's say VM1 runs on here, VM2 runs on here. Again, no problems. Use is there, 100, run is 100. And here you would see a difference is you see 2 cores, both the cores are using 100%, and there is 0 for the logical CPU because we are not using the logical CPU, one of the logical CPUs. We are just placing them on 2 different physical cores. Now this is the default ESX behavior. We try to put the VMs as much as possible on separate physical cores, and we try to avoid core sharing. But you're not going to run only 2 VMs on your host, right? Let's say you're running 4 VMs in this case. When you run 4 VMs, first VM gets placed here, second VM gets placed here, third VM comes here, and fourth VM. So now there is some sort of core sharing going on. Your 2 VMs are running and using the underlying physical core, even though there are 2 separate execution units. So you won't see ready time because they're running on the execution units, but they're sharing the underlying physical core. So in this case, what happens is the used value is low, the run value is close to 100. So you're running all the time because you have an execution unit where you can run on. But your used value is low because the used is measured with reference to the capacity of the processor. So if the capacity of the processor is 3 GHz, you're not using the entire clock cycle for one particular VM. You're kind of sharing them with another VM. So that's why the accounting changes in this case. And again, you see here only 1 core is getting used and 2 physical cores are running at 100%. Util is running at 100% here because util is with reference to the current clock frequency, so that will be at 100. But its used is less because you're doing core sharing. So this kind of explains the concept I was explaining before, how the measurement references are different between used and util and how that can come into play under various scenarios. So core sharing is not a problem you have to worry about because if you're consolidating VMs, core sharing will bound to happen. It's better to schedule the VM than not having the VM and having the VM to wait for getting scheduled. So enabling hyperthreading is a strong recommendation we always give. But there might be occasionally few workloads which might be very sensitive to core sharing. In that case, we actually provide a control option in vCenter. You could have 3 different ways where you can control the core sharing options. So you can say for a VM, do not do any core sharing. That's the none option. If you do this, we always try to place this VM only when on a physical core if one of the logical CPUs is not used. That's when we will schedule them. Otherwise, we'll put them in ready state. We won't schedule them. The default is any, which means we don't care. We just schedule it anywhere the PCP is available. We just schedule it. There's a third option called internal, which says that we will schedule them only for, we'll do core sharing only for 2 VCPs of the same VM. So if 2 VCPs of the same VM wants to run, we might be running them on 2 PCPUs of the same physical core, but we won't share this with a different physical VM. That's the third option. Anyway, so these are our advanced options. You can actually go and read more about it in you could find a help page in the UI which explains this in a little bit more detail. But I just wanted to put it out here because this affects how we schedule this VM with reference to the core sharing examples I was talking before. The next topic I'm going to talk about is called host cache. So there are two types of host cache. The first kind of host cache is called swap to SSD. This is a feature we introduced, I believe, in the last version of ESX. So here there's a VM. It's running at 70%, and it's accumulating 30% wait time. And it's not any wait time, it's VM wait. So VM wait means this VM is being blocked from running for whatever reason. So you have to pay more attention to VM wait than this wait time. This wait time could be extremely high, that's okay. But if you see VM wait, that means a vCPU is blocked from running for whatever reason. So what was happening in this case is the VM was swapping. And when it was swapping, you will see the swap counters going. Swap reads and swap writes, you see some activity going on there. But what you also notice is there's a separate counter for swapping into the SSD device. And that counter is 0, which means I'm not using the SSD device for swapping. Why? Because you can actually now go to the UI and add an SSD drive as your swap medium. Otherwise, swapping will happen on your traditional storage disk, which is going to be extremely slow compared to the SSD drives. So that's why now we provide this option to say, if swapping happens, use the SSD drive, do not use your regular disk. Let's say when you had this storage option in the in the setting here, now you see these counters, swap to SSD counters getting incremented. So you know that the swap device that you specified, the SSD device that you specified is getting used for swapping. Now there's a significant drop in VM wait. So previously you saw 30% of VM wait. The VM is getting blocked because the disk was so slow that we have to block the VM more. Now the SSD drive is so fast that we don't have to block the VM for a long time, so the wait time drops significantly. And the runtime also improves significantly. So this goes to show how important it is that if you have an SSD device, to leverage it for swap to SSD, because this will give you a tremendous boost in performance if you're doing memory overcommitment. The second kind of cache that I want to talk about is called Storage Accelerator. That's a marketing term. The internal name is called CBRC, which stands for Content-Based Read Cache. What this does is, if you enable this option in View Composer, it sets aside 2 gigs of memory in ESX and uses that memory for caching disk blocks. So this is useful when you're doing power on operations for a VM. Let's say you have 5 VM, desktop 1 is already powered on, so it's running there. And let's say you want to power on the remaining desktop 2 to desktop 5, and you want to do a bulk power on. Now since desktop 1 is already powered on, this is all like, all these desktops have identical disk images. The operating system disk is all identical. It's the same image, right? So these guys are going to read back from the disk. They need to read the operating system image again from the disk and to bring it back to memory. So when this option gets enabled, we cache them. We cache them in memory so that these guys don't have to go and hit the disk, but all the I/O blocks are in the memory, so they can power on pretty quickly. So you can actually observe this in ESX. So if you go to the disk screen in ESX, there's a way to see the I/O from a virtual machine perspective. So if you press V, it takes you to the screen where it shows I/O from a virtual machine perspective. So that is the screen. So you see all the 5 desktop VMs. And this VM is already booted up. It's idle, so it's not doing a lot of I/O. The remaining 4 VMs are doing a ton of I/O. They're doing like 23 megabytes reads per second because they're booting, and they're accessing all their disk contents. So if you add them up, it's like 100 megabytes per second on your data store. Now this is only for 5 VMs. Imagine doing this for 50 VMs or for 100 VMs. The amount of disk I/O you need on the storage. When you go to the LUN perspective, that is when you look for I/O from the data store perspective, you see there's very little I/O is done because everything is getting cached. So this kind of gives you the idea that how much I/O we save when you enable this feature called host caching. And this is introduced in View 5.1, and you need to have ESX version 5.0 or 5.1. Okay, so the last feature that I want to talk about is called SRIOV. So this is a new feature introduced in 5.1. So what SRIOV does is, you have a physical NIC. Why don't you virtualize the physical NIC? So the NIC vendors are now started to virtualize these NICs, and they provide something called as virtual functions. So they provide multiple virtual physical NICs for a single physical NIC. So these virtual functions now could be exposed into the guest operating system as a pass-through device. And when you do that, the guest operating system now would see your regular VMXNet device, which is a completely virtual NIC, and also see this virtual function NICs. Like, for example, it'll see them as the actual Intel NIC or whichever vendor's NIC you're using. And you can also see they'll be termed as virtual functions. So these are devices which are passed through directly into the guest OS. Now, there's one caveat with this, right? Anytime you do any pass-through to the guest OS, you're going to lose the mobility. You cannot vMotion this VM, because if you vMotion on the other side, you may not have a NIC through which you can do the pass-through. So this feature is useful when you're doing heavy IO-intensive workloads, where reducing CPU usage is kind of paramount important, and also reducing the latency is very important, and you're willing to trade off the mobility aspect of the VM. So when this feature is enabled, how does IO stats look from a networking screen? So if you go to the network screen, you see two different NICs here. This is for the Red Hat VM. And you don't see the third one. So these two NIC stats are for the virtual NICs. You don't see the stats for the device that is passed through the guest operating system. That's because it's a pass-through device. If it's passed through, you need to rely on the stats within the guest OS. So you lose visibility also when you use SROV. But the nice thing about ESXtop is there is other ways you can infer what's going on. So let's say you have a pass-through device and you're doing a lot of I/O into that pass-through device. First thing is you will notice CPU usage. So that will give you some indication that some I/O is happening and is using some CPU. But more importantly, if you go to the interrupt screen, if you go to the interrupt screen, you can actually see the number of interrupts processed for this pass-through device. So there's a field called PCIP, which stands for PCI pass-through. And that count will increment every time the pass-through device is being used and we forward an interrupt to the pass-through device. So this gives you a proxy as to how much I/O is happening through the pass-through device. Even though we don't have exact visibility in terms of packets, we know how many times we forwarded inputs, and usually we forward interrupts when there is some I/O activity going on. With that, I conclude my talk, and I would be happy to take questions either in the mic, or you can also come towards the stage and I can answer the questions.